Can you hear me now? We're gonna see if this works. Might be getting some feedback from the camera here. Let me know if that's okay. Anybody hear me? Alright, sounds like you guys can hear me. Woo! So much fun trying to get a mentor program going with all the technical difficulties. I'm going to blame it on the current condition of the world in 2020 and all the joys that it's brought to us. So, Ryan Cloutier tonight. I'm going to be your instructor. I'm filling in for Evan. He's unfortunately had some technical issues. Is the audio better now? Just double checking. Perfect. Cool. So, we're going to rock it out tonight. Some good content. We're going to be getting into class 11 here. First and foremost, I do just want to take a second to ask everybody, if they're okay. I know I can't hear you respond, but it's been a really trying and difficult weekend, and just know that my heart goes out to everyone that's been impacted by the events of the last week and the weekend and all these things with COVID. Know that is not far from my mind or my heart. So with that, let's quick reminder on the chat. Let's try to keep it all above board. Make sure that we're doing the right things here, and try to keep it not political. I'd appreciate that. So we're going to go through 122 slides tonight, I think. Full disclaimer, haven't actually looked at the deck yet, so you guys are going to get to see this right along with me. But it should be pretty straightforward stuff. And again, appreciate everybody's patience from last week with the technical issues that we had. And then let me know too if the camera starts to cause too much buffering or drag things down. So let's dive in with a quick refresher quiz. So we have what type of backup is typically obtained during the response, aka containment phase of incident response? Is it an incremental backup? Is it a full backup? Is it differential? Or is it binary? And if you recall, incremental backups are backups that are lots of small backups that are made incrementally over time. A full backup is a complete snapshot. A differential is going to be what has changed, and a binary is going to be an exact copy, a 100% accurate copy of the backup that we want to do. And in this case, we want to do a binary backup. We want to make sure that we have a binary backup so that we can do the proper investigations needed, and we've preserved the evidence in its purest state and form. That'll help us as we kind of navigate through. Second one is, what is the primary goal of disaster recovery planning? Are you looking to achieve the integrity of the data? Is it that you want preservation of business capital? Is the goal that it is restoration of business processes? Or is the goal safety of personnel? And as I look at this, obviously all of these things are good things, but there's one that jumps out to me as being far more important than all the others, and that is physical safety, right? The safety of personnel in all aspects of the work we do trumps everything. So when we're talking about the primary goal of planning for disaster, it's ensuring the safety of our personnel first as a primary objective, and then everything else kind of comes secondarily and tertiary to that. Next question, is what business processes can be used to determine the outer bound of the maximum tolerable downtime? So we've got, account receivable processes, invoicing processes, payroll processes, or shipments of goods. And in this, we want to think about, what's a good business process here that's going to help us define those outer bounds. For most of us, it's the paycheck. If the paycheck doesn't show up, that's going to be a big event for the company. It's going to cause all kinds of grief and issues. And so that can be a good business process to determine kind of those outer bounds of the maximum tolerable downtime. You don't get a paycheck, you might not come to work the next day. Your maximum tolerable downtime is 48 hours. What is the most cost-effective alternative site choice? Is it a cold site, a hot site, a redundant site, or a warm site? So the two things we want to think about in this question is that we've already got an established maximum tolerable downtime. So we know we have to have things recovered within 48 hours. Knowing that helps us to look at this list and say, well, a cold site probably is not the right answer. It's more than likely going to take us more than 48 hours to get a cold site to a recoverable position. If we think about the second data element here, what is most cost effective? So that gives us another piece of info to answer our question. And we know that hot sites are super expensive and redundants are the most expensive. So in this instance, the correct answer is going to be warm. And we want to make sure that, as we look at these questions in the exam, and the whole point of doing these quizzes is to get you comfortable with the kind of questions that you're going to see. A lot of these, specifically this one, is common to things that I saw when I was taking the exam. And so being able to kind of tease apart the data elements to answer the right answer is really a helpful technique. A structured walkthrough test is also known as what kind of test? Is it a checklist, a simulation, a tabletop, or a walkthrough drill? So here again, we're thinking structured walkthrough, okay? So it isn't just a regular walkthrough, and it sounds like it's more intense than a checklist. It might be simulation or tabletop. And in this case, it's tabletop. I've heard it referred to as simulation. It can be sometimes interchangeable, but the correct answer is tabletop exercise. Which type of backup will include only those files that have changed since the most recent full backup? So is that going to be a full? Well, no, because that's already going to have everything in it. A differential will have things that have changed in it. An incremental will have things that have changed in it. And a binary is a full snapshot of the whole thing. So it's either differential or incremental. And as I think about that, it says, the question asks me, will include only those files that have changed since the most recent full backup. In this case, that's going to be differential. Incremental is going to change as the data evolves on whatever schedule that incremental is set up on. So in this question, you have what you need to arrive at the correct answer, that it is differential, because it is the backup that only includes files that have changed since the most recent. So hopefully you guys are still with me. Audio's working good, video's working good. I don't see anybody complaining, which will be a first for the day. So anyways, Chapter 8. We're going to dive into Domain 7 around security operations, foundations, concepts, investigation, incident management, disaster recovery. Why do I feel like we've already covered Chapter 8? Moderators, am I on the right deck here? Feel like we've covered this. I could be wrong. I'm waiting for some feedback here. I just went with what they sent me, so you'll have to bear with me for a second here while I make sure I'm actually showing you the correct content. I think this is the right deck. Alright, so I'm just going to go on like it is until somebody tells me different. It looks like this is the right one based on what I just got. So executive succession planning. So one of the things we want to always kind of keep in mind as part of our planning is to account for the fact that eventually new blood will come in from below, and folks will have achieved the successful career. They will move on to new roles, new opportunities. In some cases, they'll move on to retirement or other such things. And in that case, we need to do succession planning. And so you want to make sure that you have an executive available to make decisions during a disaster. Succession planning is also, in the event that someone is not available. It looks like we are finishing 7 to move on to 8. So I'm just going to keep going, and you guys hit me up if I'm on the wrong thing here. So a common mistake is allowing the entire executive team to be offsite at distant meetings. I'll give you an example from a colleague of mine. Right when COVID hit, they had already had a rule that said that no more than 2 executives could be on the same airplane at the same time. And when COVID hit, they actually modified that to be even more aggressive and said that no more than 2 executives could travel within any given week, because they were concerned that they wouldn't have enough executives available, in the event they needed to deal with a crisis. And so, one of the simplest executive powers is the ability to endorse checks and to procure money. So you want to make sure you have the right people available at the right level of authority in the event that you're processing a disaster, so that you can get the resources that you need. Another important part here is getting the plan approved. So now that you've kind of developed the initial plan and you have it completed, the plan really doesn't begin to have true value until it's fully endorsed by senior management. You really do need that full buy-in in writing, because it's first and foremost, it's their responsibility. But also, if they own the plan, they feel that they have an ownership stake in the plan, they're going to be more driven to want to see that plan succeed. They're going to ensure you have adequate funding, and the other support mechanisms that you're going to need to be successful in executing the plan. Backups and availability. So super important. We're covering it again because it's super important. Having good backups, known, trusted, secure backups, is a super critical component to being able to successfully recover. You can have a lot of times we skip over, or we don't do the due diligence or do care to verify backups. So we can find ourselves in situations where we have backup files that are corrupted, or in other way, shape, or form damaged or incomplete, and that's really going to impede us as we try to go through a recovery exercise. So we want to make sure we're verifying those backups as well. It's highly advisable. It is testable. Critical backup media must be stored off-site. If you have a large enough disaster, if you don't have your backup media off-site, you'll find yourself in an unrecoverable situation. You want to make sure that the organization can quickly procure large high-end tape drives if necessary, or large storage. Tape is making a comeback, but you want to make sure that you can adequately acquire what you need to from a storage perspective in the event that you have to do restorations, or you have to do validations on this data. There could be reasons to make multiple copies, so just know that. And then if the mean time to restoration is greater than the mean time of disruption, then you should look at some type of alternative backup that will help you to get recovered more quickly. You never want the fix to be more costly or more time consuming than the problem. Hard copy data. So hard copy data, super important, often overlooked. You definitely want to make sure that you have alternative communication mechanisms, that those phone lists are stored in a format other than just electronic or just on the corporate network. It's always advisable to have a copy of your plan actually printed out and stored off-site somewhere in a secured, fire safe. Especially those call trees. I've seen issues before where organizations have not taken the step of having that hard copy paper only contact tree, and then they find themselves in a crisis and they don't know who's got whose cell phone number, and it just becomes it contributes to the disaster going on longer and inhibits them from recovering quickly. So you want to have backups of an electronic nature. You want to make sure that you have electronic as well as hard copy. Obviously, to do hard copy for your data is pretty impractical. You would end up with a forest worth of printouts. But you do want to make sure you're doing a full backup, and you want to do that somewhat often. But the big thing here, again, if it's orange, memorize it. It's full backups. They're the most time-consuming. They're also the most resource-intensive, but they are the most complete. Incrementals are only going to be archiving those changes since the last incremental or last full, and differentials will have everything since the last full. Electronic vaulting. So this is, I've heard this referred to before as like a forensic black box. Right, it's you're transferring bulk information to an offsite facility. You're going to store that sensitive data offsite. You can route out there if you need to. Generally, this is going to go over the regular internet unless you've already got some type of direct wired connection, you got an MPLS in place, or you've got some kind of dedicated circuit. If you don't, then most likely you're going to route across the internet. So it's important to remember that those communications need to be secured. As you transmit those backups, you want to make sure you're not inadvertently exposing the sensitive data because you don't have adequate encryption around them during transmission. Remote journaling. This is going to be the database journal that contains a log of all database transactions. So this goes to things like integrity, right? You want to show who made what modifications to the data and when. Remote journaling is a good way to do that. It just kind of tracks those database changes and who made them, depending on how you set up your logs. You can use it to reconstruct. So in the event of a database failure, you can actually use it to reconstruct the data changes that have been made. And it saves on database checkpoints and saves the checkpoints and journal to an offsite. So remote journaling is basically taking those logs and database changes and then storing them at an offsite location. Then you have database shadowing, and that's going to be 2 or more identical databases that are updated simultaneously. If you have real-time replication, that's going to be basically the same thing as data shadowing is real-time replication. It can exist locally, but ideally your shadow copy should live somewhere else. You should try, if you're going to use these mechanisms, you might as well take advantage of the additional benefit you get from having that data stored off-site and do that. And then database shadowing is going to allow for a more timely recovery than with just journaling alone. Software escrow. So this is the maintaining the ability of the application even if the vendor that developed the software initially goes out of business. So this is something that you can actually set up in your terms and your contracts upon negotiation with getting into a relationship with these vendors, is that you can ask that their source code be held in escrow. Generally that's done by a neutral third party. And that way, if for some reason the really cool startup that you're doing business with that has this really cool feature that you've now built your business process around suddenly gets bought up and closed or goes out of business or something else happens, then you then get the opportunity to have access to that source code in escrow and as well as any kind of purchasing of that. So something important to know, software escrow, you want to make sure that you understand this. And again, it's used primarily in contracts to ensure continuity of service. DRP testing, training, and awareness. So like the bullet point says, skipping this stuff is a huge, huge issue, and it is one of the most common mistakes, and it's why people find themselves in a DR scenario where they have a plan, yet none of the plan seems to work. Well, it's because it wasn't tested, right? Disaster recovery plan is never complete. This is a continual, ongoing type of planning. The example I'll use is a lot of organizations were not planning for a riot or riots in the middle of a pandemic. And while Pandemic Riot sounds like a great band name, it does make for an interesting disaster recovery scenario. And we did have certain institutions that have been directly impacted and needed to invoke DR as a direct result of the things that were happening that they didn't account for in their plan. They didn't have it in their plan. So I think we're all as a world learning a lot as we watch 2020 unfold, and so I encourage you guys to take that back to your DR plan. Use it to correct mistakes, right? So just because you planned for it, if reality shows you that through testing that's not what happens, gives you a chance to go back and adjust. So make sure you test for scenarios that are realistic and maybe 1 or 2 that might seem far-fetched. But definitely, run these tests and trainings. Make sure people are aware of what's going on. Make sure that, everybody knows their role to play within the DR scenario. There, are going to be some things that are going to be more complex. It's really important to test all that. Order of operations is important to test to make sure that the plan can be executed on in the way that you intended to when you created it. Again, test it. You got to test it. You need to test out what's going on. So continuous or at least frequent DR planning is a great idea. I myself had the pleasure once of doing a DR plan that involved me randomly pulling some wires out of the switch and seeing what happened. I don't necessarily advise you to start with that kind of planning. Do it on paper first, but make sure that you're thoroughly testing, what happens if, and make sure that what you're testing is in your plan, and that your response holds up as you expected, that the types of tests that you do, you get the results that you're expecting, and if you don't, go back and adjust your plan to reflect reality. You should do this at an annual basis, at a bare minimum. I know a lot of organizations that do this on a quarterly and in some cases a weekly basis. So DRP review is the most basic form of DRP, disaster recovery planning, of testing it, is to do, look at it. Does it look like, what's in it? Tabletop is kind of another way. But basically you go through the DRP and make sure that you understand it, that it's complete, that it covers all the areas. Have it done by team members who can point out any flaws in the plan or gaps that might exist. And you also have a checklist, right? This is also known as consistency testing. So you list out all the required components that you need to recover, and make sure that those are available. A lot of times, there's a lot of complexity that goes into recovering, and the type of disaster you have will kind of dictate the type of things you're going to need in order to the components you'll need to actually recover. If you have a loss of power disaster, having a generator is going to be a component that you're going to need. Having gas for that generator, having a working spark plug for that generator, all necessary components in order to be able to do a successful recovery from a power loss. So make sure your organization has the ability to acquire the assets needed and the systems and components needed within a timely fashion, aligned to your recovery objectives. Parallel processing. So this is common in environments where transactional data is the key component of critical business processing. So data is really what makes your business run. You're generally going to have some type of critical processing components, and you'll be able to do a quick recovery from previous backup. Generally, these types of parallel processing things you're gonna run a secondary site. Maybe it's warm, maybe it's a complete replicate, but you're able to do that without interrupting your production system. So you can test these out, be able to do that, and then you basically keep it up to date with the transactions from the day after backup. Then they run that to make sure you achieve the same results. So the bullet point here tells me that this is more focused upon mainframe and mid-range. They're generally going to deploy this type of test. You're probably not going to see this a lot in a cloud environment. Partial and complete business interruption. So this type of test can actually be the cause of a disaster. So extreme caution should be exercised before attempting an actual interruption test. That's what I was referring to earlier, where I actually pulled wires physically out of a switch. That was an actual interruption test to see how the system behaved. That organization was very prepared for that type of invasive and aggressive test. So you will interrupt normal business at the primary location. You will start to leverage those secondary resources in real world. Another way to call this is real world testing, right? We just took it from paper that we read, we took it from tabletop that we simulated and practiced. Here we're actually doing the actual recreation of the disaster, moving facilities, moving data, moving humans, interrupting services, so on and so forth. You want to continue to train against this. For example, that generator example I just used, same thing. Does everybody know how to fire the generator up that needs to know how to fire it up? Folks, have they been trained on their role, their specific components they're responsible for, the actual testing of and training of the things they need to do. You want to test your emergency power. That's an important thing to test for, right? You want to do a calling tree test. Make sure people know who to call. Are they going to be able to answer the phone? Is text your preferred method in a crisis? And if so, are texts getting through or people responding? So you want to make sure that your escalation trees and your calling trees work because you actually tested them. And then Even for those members that don't really have an active role or a very minor role to play in the recovery process, you really need to make sure that folks are aware of what's going on, that you have prioritized safety, physical safety, and business viability, and that the actions and steps you're taking to mitigate this disaster, to ensure those things. So make sure that folks are aware, and you communicate, in some cases over communicate, depending on the nature of who those folks are. Now you got to go into kind of a continued operations state. You want to make sure that you're keeping the business continuity and disaster recovery plan up to date. One of the biggest failures that I've seen in my time doing this job in organizations is that if they do have a plan in place, a lot of times that plan is pretty out of date. It doesn't account for all this new tech that they've onboarded, or this other tech that they've maybe deprecated and offboarded out of the environment. So a lot of times I've found that the plans are inconsistent, and that's because they weren't given continued maintenance. People didn't make it a priority to update that. And a big part of that is change management. So making sure that you can accurately and adequately track change through your environment is such an important part of your disaster recovery and business continuity process. You want to ensure that these changes are audible. You want to make sure that when you make these changes that you understand the impact that has been documented. The lack of change management can actually cause a disaster. If anybody remembers applying some Microsoft patches from previous life, right? Because those patches, or if those patches got applied without testing, you probably found yourself in a disaster-ish type scenario. So you want to make sure that you test these things, that you understand their impact, and then you want to make sure that a business continuity representative is part of the change control board and identifies any change that is proposed that would have an impact to the DCP or DRP. So if the change being proposed is going to have an impact to that business continuity plan or disaster recovery plan, that's that time to make those adjustments and to talk about that. So some of the common mistakes that we see are not getting that leadership buy-in. So important to have leadership buy-in. Not actually involving the business. So trying to design a plan for the business without their involvement. That almost certainly is going to result in some type of additional disaster, political or otherwise. Lack of prioritization among the critical staff. This can become especially painful in environments where you have multiple business units or multiple business drivers. So it's important to get this stuff figured out up front because you don't want the 3 most critical data resources you have being tasked out by different levels of business with equal pull. Having too narrow of a scope, but a lot of times it can be too narrow or too broad, but not having the correct level of scope can definitely contribute to a poorly developed BCP or DR, or affect the ability to actually use it to react and respond. Not managing telecommunications, so not having enough communications, and in some cases not having enough communications equipment or knowing what you need to do there. Supply chain management, this is a big one. COVID has really highlighted this, so this actually should be something that you think about as you do BCP and DRP. Is what are those gaps that have now been created because of external forces on the supply chain? Incomplete or inadequate crisis management plan. So not knowing how you're going to go about dealing with this, which is slightly separate from the actual doings of dealing with it. Not testing, it's so huge. Lack of training, and again, not keeping it up to date. It's so important to keep the plan up to date, and it's orange, and it's testable, so remember it. Alright, so there are some specific business continuity and disaster recovery planning frameworks that you can use. NIST 834, you have ISO IEC 27031, and BCI. The 834 is the one I'm probably most familiar with. I like it. I think it's pretty good. ISO, obviously, as part of the 27000 series, has this BCP DRP. Know this. Know that they exist. Know that there's more than one framework. I'm not going to read all this to you guys, but just know that it's there. This particular ISO series focuses just on the BCP, and the DRP BCP and the DRP is actually handled by a different framework. The key terms here are the ICT, so the information and communications technology, and the ISMS, information security management system. They have a separate ISO plan, so that's ISO IEC 24762, circa 2008 it looks like, or sub 2008, I don't know, I'm not a big ISO guy, I'll be the first to admit it. Then you got our good old British standards, right? Because you got to have a little BS in your life. So it's 25999, and it's basically got part 1, which is the code of practice. So that's going to be around the business continuity management, best practices, best recommendations. Again, guidance only. Very important to understand that, guidance only. Part 2 is going to be the actual requirements for the business continuity management system based on the business continuity management best practice. This is the part of the standard that you use to actually demonstrate compliance when you audit against it as part of the certification process. BCI, which is the Business Continuity Institute, published their 6-step good practice guide. Looks like in 2008, refined it in 2013, and it describes business continuity management process as management practices and technical practices. So it breaks it up into 2. Under management, you've got your policy and program, and then how do you embed the business continuity. Under technical, you have analysis, design, implementation, and validation. So the actual nuts and bolts, how are you going about doing this? All right, so Chapter 8 is in the bag. Domain 7 done. It says something about break time. I think you guys have been pretty hardcore as we've gone through this. Everybody good? I don't see a lot of chat. I think we're good. I'll just keep cruising unless somebody needs a potty break. And if you do, you're an adult. Get up and go get one. All right, so moving on to Chapter 9, Domain 8, Software Development Security. Understanding, applying, and enforcing software security. I have such a passion for this because this is where the bugs come from, right? By not having a security mindset. So this is our last domain. I hope you guys are getting excited. I'm gonna go through this at a pretty good clip. But just know this is it. You guys are nearing the finish line of the domains, and hopefully you're as excited to be done as I think we are to be excited to have you done, because we want to see you get out there and get your certification when the world reopens. All right, so we're going to talk about programming concepts, application development methods, databases, object-oriented design and programming, assessing the effectiveness of software security, and the artificial intelligence, right? Because that's the thing now these days. So we're over some terms and definitions. So extreme programming. I don't know how many of you are familiar with the concept of agile development, but it's a development method, and it comes in several flavors. And one of those flavors is extreme programming, and that's going to use a pair of programmers who work off of a very detailed specification. Object is just a black box that combines code and data and sends and receives messages, so an object could be anything. Object-oriented programming is a programming methodology that gets away from kind of the line-based programming of the days of old, that procedural programming, do this, then do this, then do this, to more of a if this is that, and this is also that, when this is like this, or do this while that's like that. So you start to get more in that object-oriented type of language structure. It's also a little bit different in the way that the relationships communicate, because you can actually have the objects send and receive messages and do these different things, including security. So there are procedural languages. Those are going to use subroutines, procedures, and functions. These are just mechanisms within the programming itself that allows you to have different types of functionality, different types of processing, if you will. So just know, again, if it's orange, you need to know it, memorize it. Spiral mode is spiral model is a software development model that's designed to control risk. So it's a development model that inherently has risk control kind of built into it to try to limit that. Systems development lifecycle is the totality of the system This is a development model that focuses on the embedding security within every phase. So a system's life cycle or an application's life cycle is the totality of that application from creation until sunset, until it is no longer supported and is terminated. This systems development lifecycle is taking that account that security needs to be present within every single phase of that lifecycle. Waterfall model, this is an older application development model. It's still used today. Honestly, if you talk to programming people, you'll find out that most everything is either what we call Scrum Fall or Wagile, which is a play on words for waterfall, because Agile has Agile and Scrum, but the reality is Waterfall still finds its place in a lot of development phases and requirements. I have yet to see anybody completely Agile. All right. So programmers on average are going to make 15 to 50 mistakes per 1,000 lines of code, and that's if they're using a programming, if they're not using any frameworks at all. If they're using a programming framework, they can actually get that mistake much lower. And so the CMM is the Software Capability Maturity Model. There's an index for that called the CMMI. I'll look at that in a second. But it is basically a method and a model to show the overall maturity of the process within the software development and how you're going about doing it. And it actually applies very neatly to the CMMC, leverages the same base concept that there is kind of this chaotic phase, and then you kind of, as you come out of that, you can increase your levels of maturity through process and control. So having said that, so CMMI, again, Carnegie Mellon, great group, same group that's putting out CMMC for the cybersecurity world. So I encourage you to look into that. It is a great concept. It basically works like this, right? So the first level is unpredictable and reactive. So you're getting work done, but there's really no control to it. You're generally, it's late, it's over budget, it's got a lot of issues. Yeah, work got done, but not at a maturity level that allows for acceleration, growth, more stuff to get done faster with less disaster. And then you have maturity level 2. So that's going to be this is a project managed type of situation. So things are generally planned, then they're done, then they're measured, and they're controlled. Level 3 maturity is getting to defined. So this is more proactive than reactive. So now you've got organizational guidance around how to do activities, how to build things, how to develop programs, how to do the kind of project management piece. Level 4 is quantitatively managed. It's measured and controlled. So it's data driven. It's using quantitative performance to improve objectives that are predictable and aligned to the needs of the stakeholders, internal and external. And then optimizing. Everything's pretty stable, but also is flexible. And this is really where you get to that continuous improvement. I've seen many organizations strive for a 5. It is a hard goalpost to hit. Okay, so here you can see, this is another breakdown of the same concept. It's basic, management controls, right? Is ad hoc. There's a little formalization. You got all kinds of tools in the toolkit. There's really no consistency. Then repeatable again. You're trying to get to kind of known results, stable results, known outcomes. Process management, is again you're continuing to refine upon that. You're increasing, the quality and cost parameters are starting to come into play. You're gathering and maintaining more data. You're kind of building those processes out. Process control, again, managed, right? You've got good quality coming out of it. It's comprehensively measured, and then optimizes is that continuous improvement. Machine code, also known as machine language. This is what the computer itself really understands. It is the ones and zeros that translate to the actual CPU code that the CPU can understand. Source code is going to be any computer language instructions that are written in text that have to be translated to machine code. So when you are writing a program and it's, hello world, and you define your variable and you populate that variable, all those instructions, when they're in that text language, not machine language, those are considered to be source code. Machine code is what happens to that after it gets translated for processing by the CPU. So here is a look at machine code. So if you're familiar with hexadecimal, but that's that. This guy here, Gary, he explains it. Good explainer. Yeah, so take a look at this. I'm sure it's in your thing. I don't know if I was supposed to play this or not, so I'm just going to move on from it. But take a look at it. It's, we'll explain assembly language and machine code. You don't necessarily need to know the deepest of the ins and outs of all of this. You do need to know these things exist, and you need to know that source code and machine code are different. Machine code's processed by the machine. Source code looks a lot like this. So again, this is kind of the code itself. These are the structures that you put this text in that ultimately gets converted. Assemblers are low-level computer assembly language, right? Is a low level, so it uses things like add, sub, jump. It's got these mnemonics, and it's trying to match, to the machine language instructions. The assembler is going to convert assembly into machine, and a disassembler tries to take the machine language and convert it back over to assembly. That's going to be when you're working with that, kind of that machine language. Compilers are going to take the source code, and they're going to try to compile it into machine code. So if you've ever done any development work, you do a build, you go to compile the code. What is it doing? It's taking all that text that you wrote in your source code, and it's trying to actually make machine-based math instructions for the CPU. Interpreters are interpreted languages, so you have different compiled languages. Shell code is compiled on the fly each time. So Perl, Python, Java, these things are interpreted language. Then you've got bytecode. So like Java, for example, is interpreted as bytecode. It's anything that is an intermediary when converted from source code, but still must be run, converted on machine code before it can actually hit the CPU. So Java Virtual Machine handles that handoff for you. Programming language generations. So we've been working on building code for a long time. First generation was machine. Second generation was assembly. So we're going up in layers, if you will. Third generation, COBOL, C, and BASIC. Fourth generation, Cold Fusion, Progress, 4GL, and Oracle reports. Fourth generation languages tend to have some type of GUI so that you can drag and drop, and they focus on the creation of database reports and websites generally. So this is another look at that. So if you have, again, human natural language, and this is where we get into like natural language processing and fifth generation intelligent languages. They use code that's more similar to our spoken word. Machine language, again, long difficult programming, ones and zeros. It's using math, it's talking in machine language. And then you have your assembly, your procedural, and your non-procedural. So kind of like this, right? Same thing, okay? So let's take a look. There's your hexadecimal, okay? That's what assembler is going to look like. That's your C, your Fortran, your C++, your Java, and then your Ruby. And as you can see, in each step it gets closer to that human language. CASE, Computer-Aided Software Engineering. So it uses programs to assist in the creation and maintenance of computer programs. There's three types of CASE software. Tools, and they're only going to support the specific task in the software production process, so whatever that particular tool is set to do. Workbenches are going to support one or a few of the software process activities. So it's a workbench is going to allow you to aggregate several tools together into a single application. Environment is going to be kind of that totality of several workbenches, several tools, and kind of that whole collection is within the environment. Top-down versus bottom-up programming. So top-down starts with the broadest, highest level requirement. So what is the final product, final program going to look like, and then you work down towards lower level technical implementation. So you start with big picture and you work down, top down, bottom up. It does the reverse. It starts with the lowest of the technical components and it builds up to the full complete program. Procedural languages like C historically have been programmed top down. You start with the main program and then you define the procedures and work down from there. Object-oriented programming generally uses bottom up. Set up your objects and then build them together. It's kind of like building a house to get your final program. Types of publicly released software: open and closed source software. Closed source is software that is typically released in an executable form. So we can think about that as like Oracle or Windows, and Microsoft's not handing you their source code. Open source software is where you can actually get the source code publicly. And good examples of this include Ubuntu, Linux, Apache, web server, GitHub. GitHub's a great place for open source. Closed source software and proprietary software are sometimes used as synonyms. That's not always true. Some open source software can be proprietary. Free software, shareware, and crippleware. So free software means that it's free, right? I don't charge you money for it. And it could also mean that you're free to use the software. Sometimes as you could modify it. There is gratis and libre respectively. So freeware is free as in beer, right? So gratis, here you go. Software and is free of charge, right? Libre allows you again to make those modifications. Shareware is usually fully functional proprietary software used free of charge. Usually comes with some kind of time limit, and they usually want some kind of payment. And then crippleware is partially functioning software, proprietary software that has like key features disabled. So if you've ever tried to use like a limited time offer on a software suite, it'll let you do 10 things, but 50 of the features are turned off. Software licensing. Almost all software has a license, whether that is open or closed source, and that license will delegate things like who's the copyright holder, what are the terms of service, what is the end user license agreement, if it's open source, what type of licensing are you allowed to do? Do you need to name the contributors? Are you able to copy paste it for commercial? Can you only do it for nonprofit, etc., etc.? GPL is the most prevalent type of open source license, and that's again that focuses on the libre side of it, right? It's allowing them to change, share, approve upon, add on, so on and so forth. So GPLs are generally wide open. Then here's an example of that, right? So Creative Commons, same thing here. They're going to let you it's got very clearly defined licensing of how you can use it, who's allowed to use it, what kind of credit do you get. Same thing. Here's another example. Same thing with the GPL. I'm not going too fast for everybody. Looks like, I think, yeah, exactly, WinRAR, somebody said, I think, in the chat. So that's a really good example. Application development methods. So waterfall, it predates software design. It was used in manufacturing, right? It's very rigid. I do this, then I do this, then I do this, then I do this, then I do this. There's really no going back. There's no iterative. It is I start at point A, and I walk through the alphabet until I get to point Z. It was used in software development the first time in 1969, but waterfall as a concept existed before that. So again, requirements, design, implementation, verification, maintenance. This is very rigid. This does not necessarily allow for when I get to here that I've learned that the requirements were off for me to go back and fix that. Hence where the modified waterfall, so back to what I was referring to when I say scrum fall or Wagile, it's some incantation of this where there's a feedback loop that actually allows you to go back and make adjustments. The Sashimi model has highly overlapped steps. It's basically a response to the waterfall. It was named after this the Japanese delicacy, sashimi, which has overlapping layers of fish. So keep that in mind. And it's based on the hardware design model used by Fuji and Xerox. This is testable, so try to remember this. And this is a visual example of the kind of overlay, if you will, of the Sashimi model. Then we have Spiral, and Spiral is again, it's everybody in the early days was trying to do a lot of stuff to try to figure out how to develop software better, because we would start building stuff and we would start to learn. Man, we didn't probably get those requirements right, or we could have done better here or there. And so, you know, this is just another flavor of that. It's generally going to follow the waterfall type of methodology, but it does a risk analysis each round. It kind of looks like this. So you can see, here we go with, kind of the prototype, and then we're checking, we're doing risk analysis. So each time as we move through this spiral, we're reassessing for risk, we're checking in as we go. And a lot of those core concepts carried over to probably the most common method now, which is Agile. And some of those methods, and I've talked about this a couple times tonight, but it's Scrum and Extreme Programming. I do encourage you to familiarize yourself with the Agile Manifesto. The core values here are that individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. Now, notice it didn't say no plan. Notice that it didn't say, no tools, right? It's about making the software work better. Doesn't mean no documentation. Doesn't mean no plan. You still have to document, you still have to plan, but just know that it allows for mechanisms to make those processes easier and more, agile. Scrum. So it's named after Scrum in the sport of rugby. It contains a very small team of developers, the Scrum team. They're supported by the senior member, who's the Scrum Master, and then in this relationship, the product owner speaks on behalf of the business unit, advocating for the changes, and the Scrum Master's job is to make sure that the Scrum teams can actually commit to and deliver on what they're able to. Extreme programming, so again, pairs of programmers, and they work on very detailed specifications. There's a high level of customer involvement. You got to know this stuff. I've seen extreme programming before, but more often than not, the Agile I've seen is probably closer to a Scrum model or a Kanban model. I don't think we'll talk about Kanban in here, but maybe. So anyways, know that XP programming is extreme programming. Know that it's a form and flavor of Agile. 40-hour work week with forecasted iterations. The idea is that you're able to get more forecast in how many hours you need to actually complete the project over time, and then the customer's highly involved. You do unit tests, so you have very detailed test procedures so that the work, the code that you get completed is thoroughly tested for all the various ways it could be used or misused, and those are called unit tests. Then you have rapid application development, RAD, right? Again, not really going to see this a whole lot, but it's basically how fast can I meet the business need, and we'll kind of, we'll keep the customer highly involved. This is about GUIs, prototypes. It's about cranking something out as quickly as possible that's semi-usable, and then you go back and see if you made good technical decisions or not. Prototyping. So prototyping is going to be the iterative approach. So we kind of create some mock-ups, some prototypes. It allows for a little bit lower risk, because the customer is able to see the product in progress before it's finished. It looks a little bit like this. So this is a rapid application with iterative prototyping. So they write some code, they publish some code. People take a look. You see here the 1 to 21 days to reevaluate. Respecify and redesign. Kind of in this 2 to 6 month larger process. Again, not necessarily going to see this in this form as much anymore, but it does exist out there. And I think a lot of prototyping has just gotten to they just use Agile because Agile already accounts for all that. Or Scrum rather. Systems development lifecycle. So back to what I was talking about before, the SDLC. This is the totality of the lifecycle. On the exam, the SDLC is going to be focused on applying security in every phase of the development cycle. If there was one thing that we as an industry and we as practitioners could do to help us have less issues, less bugs, less 0 days, less things to be exploited, it would be by implementing security into every phase of the development lifecycle. It's going to be broader than many application development models. It's going to focus on the whole system, from selection through development through operational requirements to secure disposal. So software development lifecycle or the system lifecycle, SDLC, again, it's all about, on the exam, it's going to be about having security in every phase and really taking that broad approach. If you look at here, the NIST 814 has been withdrawn, but it broke it up kind of as operation and maintenance and disposal, and I believe this has been replaced by 34, I think it was. So anyways, systems development lifecycle, it's not testable. Evan apparently likes the OWASP, Secure Software Development Lifecycle Project. I agree. I think secure software development is key. Take a look at that if you get a chance. That's not on the exam. Let's see what we got here. The text from the DOJ SDLC graphic. So I'll let you chew on this for a half a second while I take a drink. I'm not going to read all that. That's an eye chart. I encourage you to study it, understand how it works. But basically, it's somebody has an idea. You figure, you kind of form that idea a little bit. You plan that idea. You figure out what it's going to take to do that idea. You actually start to write down and design how you're going to go about doing it. Development is doing it. Then you check to see, did what I think I did actually work the way I thought it would? And then it's about implementing it, rolling it out, getting it out to the world. Once you release a product or code or anything like that, you got to take care of it. You got to maintain it, and then ultimately, all things have an end of life. All things pass away. All things cease to be technologically valid, and so you have disposition. More on software escrow. So again, it's if the vendor doesn't want to share with you, that is perfectly acceptable. They don't want to share their source code, but that's where software escrow is going to come into place. So again, you want to put the code in escrow, and it's under the control of a neutral third party. So you don't get to access anything until that company has an issue that allows for the contract terms of that escrow to grant you access to that source code in the event that they, for example, go out of business and you're dependent on their code. And we have seen this many times in the software industry, so know that it's very important to have that. And generally it's because the business doesn't succeed and fails, or it is acquired by a larger organization who's potentially a competitor or something else, and they just want to shut it down. Code repository security. Please secure your GitHub. I beg you, secure your GitHub. Nothing worse in the world. Well, I suppose there are many worse things in the world. A very bad thing that we do is we leave our GitHub unprotected when we have code in there that could be weaponized or used against us. It's the accidental publishing of private code is public. GitHub's great, love to share all that source code and share it openly, but if it's private, we need to really keep it locked up. We don't want to be publishing our passwords, we don't want to be sharing our private keys. So thinking about the security controls we want to have, system security, operational security, software security, communication security, file and system backups. How are the employees accessing things? How are we going to maintain security? And any credit card data that we might also need to keep safe. Apparently, if you go to page 448 of your book, there's a really great story on this. APIs, so simple application programming interfaces, right? So we want to secure those because APIs are they're a way into the code, right? It's exactly what it says it is. It's an application programming interface. So if I gain access to an API I'm not authorized to, I'm able to manipulate and make modifications to that program and cause unintended things to happen, to be able to steal data, just wreak havoc and generally be a bad guy. So make sure that, securing those APIs is super important. We want to make sure we're doing that because we're trying to limit that risk. Software change configuration management, again, super important. The exam will treat them as different. So the exam will treat configuration management and change management as separate activities. They are one of the same whole. They are very related disciplines. Configuration management tracks changes to a specific piece of software. Change management tracks changes across a software development program. So configuration management, narrow scope. Change management, broad scope. It's another way to think about it. Software change configuration management, so more on this. NIST has a special publication, 8128, the Guide for Security-Focused Configuration Management of Information Systems. Configuration Management Plan, or CM Plan, is going to describe the roles, responsibilities, policies, procedures, who's doing what and what is expected of them, and what are they responsible for and what are they authorized for. And then you have the Configuration Control Board. So that's going to be a group who comes together, the group of qualified people who basically make the judgment calls as to what the impact of those changes could be, and should they be done, and are there additional questions that need to be asked, etc., etc. Configuration item identification. This is getting very granular. This is how you select and name the configuration items underneath the configuration management plan. Configuration change control. So this is the process for managing updates to the baseline configurations. So easiest way to think about this is like Windows operating system. You get it out of the box, and if you want to secure it, you start applying all the patches, you get all this stuff. Once you have it up to date, you want to roll it out to your environment. That's your baseline. Then as you roll it out to your environment, a week later a new patch comes out and you make that adjustment. You add that patch to your new gold image, if you will, your new baseline image. You've then changed the configuration. So that's what that's referring to as configuration change control, is having the process for managing those updates to those baseline configurations. And configuration monitoring. And actually this is a great mechanism for detecting deviation. So if you actually monitor for deviation of the configuration, a lot of times that can be a threat indicator as well. But you want to monitor for that. You want to make sure that things aren't changing when you don't want them to be changing. Whether that's within your configuration items or within the configuration baselines, or really anything that moves without you expecting it to. DevOps. DevOps is the result of an internet meme that I love, where the house is on fire and the developer and the little girl's in front of it, and it says, "It's ops problem now." And that stems from this old two-siloed system of the past, where you had development on one side of a fence and you had ops on the other, and back and forth, and fought like cats and dogs. It was insanity. And so DevOps started to emerge to say, wait a second, we're two parts of the same whole. We would like less buggy code. We want more stable code. The developers are like, great, we want you to actually configure the systems in the way that works with the code. And so DevOps kind of came together to help actually have successful releases, instead of developer writes a build, pushes it out, operations guy applies the build, something breaks, he rolls it back, sends it back to the developer, says fix your broken code, without actually explaining, maybe in some cases, what really went wrong. So it's about working together, getting rid of silos, and trying to really participate throughout the entire life cycle, so that the developers and the operations engineers are on the same page. Object-oriented design and programming. So object-oriented design and programming is going to use the object metaphor to design and write computer programs. Object-oriented programming replicates the use of objects in computer programs. Object-oriented design treats objects as a higher level design concept, like a flow chart. Again, study this stuff, know this stuff. One of the best ways it was ever explained to me to understand object-oriented programming was to think of a house. And within the house, each thing has a function. Each thing was a thing before it was a thing. So for example, a door starts out life as a tree. The root object of door is tree, then there's processes that happen to it to make it to a door. Then a door has functions before it can be used in a house, like hinges and knobs, and those knobs turn. and those are the functions, right? So if the door is the class, the hinges are a function, the knob is to turn it to the right is a method, to turn it to the left is a method, and door open and closed is a function. So it's just one way to think about it. Object-oriented programming. So again, treats the program as a series of connected objects that communicate via messages. It does try to attempt to model the real world. OOP is probably among the most commonly used programming out there now. Java, C++, Smalltalk, Ruby, C#, F#. I mean, there's 50 different flavors. An object is a black box that is able to perform functions and sends and receives messages. Objects can contain data and methods. And the methods are the functions they perform. So back to that, I turn the knob to the left, the door opens, the latch goes away. Those are all functions within that doorknob object. The object provides encapsulation, can also hide that data, because outside we don't really know what the object's doing to that data from the outside. Cornerstone object-oriented programming concepts. So cornerstone object-oriented programming concepts include objects, methods, messages, inheritance, delegation, polymorphism, and drum roll please, polyinstantiation. A lot of terms here, not going to unpack them. Getting a little dry in the throat actually. Not going to unpack all that, but memorize those. Objects are things. Methods are things that objects can do. Messages are how those objects communicate. Inheritance is the idea that just like I've inherited something from my parent, an object can have a parent and child relationship and inherit something from that. It's a way to reuse code. Delegation is one object relying on another to provide specific functionality. So I delegate the math that my app needs to do to the math function or the math object. Polymorphism is the ability to create a variable or function or object that has more than one form. Metadata is a great example of that. Polyinstantiation, just means many instances, right? So it's having two instances of specific objects with the same names that have different data. And we'll get a little bit more into that here, I think, in a second. So again, using messages to communicate. So you have an object that wants to communicate to another object. It uses message, it sends a message to that to interact with the method. This could be things like, change the font. This data says, somebody clicks and says, I want to change a font size. The mouse object communicates to the data font object and says, method 1 is change font size. So hopefully I'm making it clear as mud for you guys and you're keeping up. I don't really know everyone's technical background, so know that you don't need to necessarily know as much as a programmer, but you really do need to understand this. This is an important domain. It's a tough one. Again, the big thing here, security and the life cycle. That's it. If you remember nothing else, security should always be part of the software life cycle. Coupling and cohesion. So here's an example of coupling versus cohesion. Cohesion, you can see we've got A directly talking to B, E's directly talking to F, and E is directly talking to G. Where coupling, A is talking to D, but also could be talking to E, could also be coupled to B, while B is now talking to F and C. So the two concepts are an object that is coupled requires a lot of other objects to perform basic functions like math, right? So if it's highly coupled. An object with high cohesion is more independent, so it can do most everything by itself. So that's the big difference, right? Coupled is going to have a lot of the functionality. Coupled is going to be relying on lots of other objects to have complete functionality. And if it has high cohesion, generally it has all those functions within it. Object request brokers can be used to locate objects. They kind of act like the object search engines. They're a form of middleware that are connecting the programs to other programs. COM, DCOM, and Corba are common object brokers. Look at that for a second. So here's your object request broker. Client says, hey, I need an object that does math. The object request broker says, oh, okay, yep, I got some math stuff. Let me find you some math objects. Oh, good, here, have that math object. So that's kind of what that's doing. Corba, which is your Common Object Request Broker Architecture. It's an open, vendor-neutral, networked object broker framework put together by the Object Management Group. It competes with Microsoft's proprietary DCOM. So, you know, they're doing the same thing, but they have slightly different flavors because they're both, one's open source, if you will, open vendor, if you will, and the other one is closed, right? So it's proprietary. So you interact slightly different, but they do the same job. Objects communicate via message interface using the interface definition language. And the essence of Corba is that, you know, beyond being a network object broker, it's the separation of the interface. So syntax for communicating with an object from the specific object or instance of the specific object itself. Here's another look at that and how that is using that. So here you have the, you know, TCP socket. You see the object request broker. Here it has the Corba library for the adapter. You know, the server on this side. You got your client over on this side. You know, the library here on the client side reaches out for that server side object, so that you don't necessarily have to have all the every last line of code on the client side. You can have library references, and it'll use the object request broker to then go and find out what it needs to grab. Object-oriented analysis, OOA, or object-oriented design, OOD. So object-oriented analysis and object-oriented design are software design methodologies that really take the concept of objects to that higher level, right? It's going up in kind of more of that conceptual level. Sometimes they combine them, OOAD, object-oriented analysis and design. You know, it's like drawing a flowchart on a whiteboard, and it's going to show you conceptually. So this is all about being at that 50,000 foot conceptual level. The way the data in the program, you know, flows and is manipulated, you do that by visualizing that with messages and objects. And once the software design is complete, the code can be programmed directly into an object-oriented programming language because the design specs fit so nicely because they were object designed. Object-oriented analysis seeks to kind of understand and analyze the problem, the challenge, you know, that you're really trying to fix, right? And it says, okay, well, how do all these objects interact, and what do they do? And so you use that to do an object-oriented design, and then you develop the solution from there. So basically, this is just high-level object-based ways of designing the application, so that it more easily fits the object-oriented programming. Software vulnerabilities testing and assurance. So this is, you know, MITRE, CWE, and SANS, right? Top 25 most dangerous software errors. Still pretty much the same as they have been. Just like with passwords and other security issues, we haven't seen the improvement we would like to. So anyways, hard-coded credentials, that's a no-no. Don't do it. Please don't do it. Buffer overflow, that's making sure that, you know, that happens when you haven't done an integrity check to make sure that the variable can actually handle the volume of data coming in. You don't want to give somebody a free text field and a variable that says I can only hold 4 things, because when that happens, you get an overflow, and then they can manipulate the code. SQL injection, that's manipulating a specific SQL statement. Directory path traversal, again, being able to escape and navigate to other places on the server because you didn't code for that correctly. TOC, TOU, and race conditions. You know, once they get the system into a race condition, that allows them to try to alter before it gets checked. Here's an example of it, right? So if the test is readable by the user, then open the test file. Else print the error, you can't open the file. Well, the race condition occurs between steps 1 and 2. So it's while we're opening test file, the computer might decide to, you know, do it like this. If the test file is readable by the user, run another process, then open the test file. So we want to make sure that we are preventing race conditions because they can be exploited. Disclosure. So disclosure is an important part, and two things to understand here, and I'm going to start actually in a backwards order because I think responsible disclosure is so important. So disclosure is when you found something wrong and you're going to let that vendor know. You're a security researcher, you found an issue, you're going to let them know. Responsible disclosure says that you're gonna do that privately, and you're going to give them adequate time to solve the problem. That you're not going to go to the public until after they have fixed the issue. Okay. Full disclosure is you just put them out on blast. You just decide to take them straight to Front Street and stick them out there and say, hey, I know that I found bugs in your system 5 minutes ago that you haven't had a chance to fix, but the whole world needs to know about this right now. And I published all the code, and I published how I did it, and I just put it out to the world. I am of the latter camp. I believe responsible disclosure, unless there is an immediate threat to human life and safety, and the vendor in question refuses to cooperate. That's the only time that I would be comfortable doing a full disclosure, just because I think they lead to more trouble than good, even though they're a lot of times done with best intention. Databases, so we're going to go over some different types of databases. Formal database types include relational, which are two-dimensional, hierarchical, and object-oriented. The simplest form of a database is a flat file. Any text file that has multiple lines in a standard format is considered a database. Here's your flat model, hierarchical model, right? So you can see the relationship structure. We have a relational model, so a lot of reference, key reference, primary and foreign key reference. You have an object-oriented model. So this is your data table. This is your data table. You have these shared codes, but not in a relational sense. So this is duplicative. This is actually shared. And then network model. So again, know this stuff. Memorize it. Relational database is the most common type of a modern database, and it's got two-dimensional tables, hence the relational term. The table itself is also called a relation. They have rows and columns. A row is a database record, or also known as a tuple, and a column is called an attribute. And like with all good IT things, we want to make this as confusing as possible, so we have 50 different ways to talk about this. But basically, in a relational system, I don't know if I've ever heard anybody call it a tuple, but I have heard columns called attributes. So, but anyways, a row is a database record, and a column is generally the attribute. A single cell is the intersection of a row and a column is the value. And relational databases require a unique value called a primary key in each tuple in a table. And the reason that is they rely on that key to ensure uniqueness in the data, and that you're not getting duplicity. And so, relational database is sorted by the primary key. I would never myself make a social security number a primary key. I just wouldn't do that. I wouldn't even use social security number in a primary key. I'm actually going to have to ask Evan what this is all about. But in this example, we are going to use it, and so we selected it because it was unique. And two tables can be joined by that social security number. So we may have a table that has the name of the person and their social security number. We could also have a table that has the role, and we use SSN to map that, to say, okay, I don't know why anybody would do this. This is a terrible example. I'm sorry. But it does, it does exist, right? You are going to find it. So basically, the primary key is what allows me to ensure uniqueness in the record across. And I can join two disparate tables, so a table of names and a table of titles. I can join them on the primary key, provided that they both have that key relationship. A foreign key is the key in the database related to the database table that matches the primary key in the parent database. So a lot of parent-child relationships in databases, and this is just another one. So that primary key that resides in table 1 has a corresponding foreign key in table 2. Referential, semantic, and entity integrity. So referential integrity means that every foreign key in a secondary table matches a primary key in the parent table. Semantic integrity But semantic integrity means that each attribute, each column value is consistent with the type, with the attribute data type. Entity integrity is that each tuple has its own unique primary key that is not null. Database normalization is the art, if you will, to try to make the data as logically concise as you can. You want to make it organized and consistent. The higher levels of normalization, and we'll get into that in just a second here, but the higher the level of the form of normalization, it's generally considered to be at most normalized. However, can actually be, in some cases, not as performant as lower levels of normalization, which gets into a whole other thing I don't think is on here, which is when do you denormalize. But anyways, what you want to do here is the idea is to try to get rid of as much redundant data and opportunity for data corruption to exist, or lack of integrity around that data. So the more you normalize the database, the idea is that you are creating a higher degree of integrity around that data because you've removed the redundancy and the chances that you might read from the wrong table. It also helps you keep all that data in sync more easy. Database views can be queried. They're the results. They are the query results of a database view. So you can create a view. You do that to constrain a user interface. So for example, I could have a table that has 1,000 columns in it, but this user only needs to see 4. So I'll make a database view for that user that only needs to see those 4 data elements. The data dictionary is the description of all the database tables. So this is going to, the metadata about the data. What's in this column? What's in this table? What do they do? What are the keys, primary keys? You're going to find all that stuff in the data dictionary. It's generally in the database schema, and it's just going to describe the values and attributes of the database table. Database query languages allow you to talk to, right? So it's the programming language of databases, if you will, or the querying language. I shouldn't say programming, so it's not, it's querying. But you have data definition language, and that's for creation, modification, deletion of tables. You have data manipulation language, which is how you pull data out and update data that is stored. The most common and popular language out there is SQL, and that's structured query language. It was created in IBM in 1974. It comes in 100 different flavors, but it pretty much all has the same basic structure of these commands, which is create, that's to create a table, to actually select a record from a table or a specific role. Delete, which is to delete a record or a whole table. Insert is like it says, it's insert, and update does exactly that. It updates and it changes a record. You have hierarchical databases that form a tree. DNS is a type of global tree hierarchical database. Object-oriented databases are going to contain, generally just passive data. Object-oriented databases work with functions, so other code, to actually, be able to produce data out into an application. Database replication and shadowing. So database replication mirrors the live database, allowing simultaneous reads and writes to multiple replicated databases by clients. Replication comes in a few different flavors. I'm not going to unpack that today, but primarily it's going to mirror it. Depends on the schedule and all that, and what type of replication, how it handles conflicts. But shadow databases are similar to replicated databases. The big difference here is that the shadow database mirrors all the changes made to a primary database, but clients do not actually access the shadow. Data warehousing and data mining. So that's a large collection of data. So anytime that you store very, very large amounts of data in a database, you start to get to a point where that's considered a data warehouse. And good Lord, excuse me, it has been a long day. Once you start pulling data out of that warehouse, it is considered to be data mining. Not when you pull it up, but when you're actually starting to look at the patterns. When you look at the patterns, that's when you're doing data mining. Artificial intelligence is the science of programming computers to think more intelligently, trying to kind of mimic what we do as humans. There's a lot of really interesting AI out there. The Terminator AI is not here yet, to the best of my knowledge, and the best AI I've seen so far is nothing more than really overblown and super fancy statistical, standard deviation and just basically stats 101 on steroids. Let's go back here. So expert systems generally have two main components. You're going to have your knowledge base, so that's all those if-then statements, and then you're going to have an inference engine that is going to kind of follow the tree that has been formed by the knowledge base, and whenever those rules match, it's going to kick something off. It's going to say, oh no, I see here that we have a match between the decision tree of if this then that, and I see that when that occurs, I should do this next step. So it sets off the rule. The integrity of the knowledge base is super critical to this. The entire knowledge base should form a logical tree beginning with a trunk. The knowledge base should then branch out. And the interference engine should follow the tree, branching and firing as it hits the if-then statements, as I answered. And you have artificial neural networks. So these simulate neural networks found in the humans and animals. We have 100 billion neurons interconnected by thousands of synapses or more. And each neuron fires based on a synaptic input. So this is a multi-layer neural network is capable of making a single decision based on thousands or more inputs. So this is kind of just another way that we're trying to mimic our own intellect, or our own biological wiring, if you will, electronically. How artificial neural networks operate. They seek to replicate the capabilities of biological neural networks. So they use a node to describe. A node is described as an artificial neuron. The nodes receive inputs from synapses and send output when the weight is exceeded. Single layer artificial neural networks have a layer of input nodes. Multi-layers have multiple layers of nodes. So again, single layer, one layer of nodes. Multiple layers, or multiples, ANN, have multiple layers of nodes, including hidden nodes. Both single and multi-layer artificial neural networks eventually trigger an output node to fire, and the output node is ultimately what makes the decision. Artificial neural networks, so it learns by example. So you have to, that's why you always hear about training the AI model. You got to do this training function. So they change the synaptic weights via an iterative process until the output node gives the correct answer for a given set of inputs. Artificial neural networks are used for fuzzy solutions where exactness is not always required or possible, such as predicting the weather. So here's a schematic of a neural network. So you can see you have your input units here all routing through. You have some hidden units, and then the actual output units when the correct criteria for activation has been met. Bayesian filtering. So Bayesian filtering is named after Thomas Bayes, an English clergyman who devised the number of probability and statistical methods using simple mathematical formula for calculating conditional probabilities. Most commonly, it's used to identify spam, and it's a filtering technique to automatically assign the probability that certain tokens, or in this case words in the email, were indications of spam. So it's just another statistical algorithm, if you will, that we apply to try to further filter and refine that data. We have genetic algorithms and programming. Genetic algorithms and programming seek to do kind of the mimic DNA, if you will. Genetic programming refers to creating entire software programs, usually in the form of Lisp. Lisp is an artificial intelligence programming language. Genetic algorithms refer to creating shorter pieces of code represented as strings called chromosomes. Genetic programming creates random programs and assigns them a task of solving a problem. The fitness function describes how well they perform their task. Crossover breeds two programs together and swaps their code. Mutation introduces random changes into some programs. So, and this is, kind of the summarization, if you will, right? Generate an initial population of random computer programs, execute each program in the population and assign it a fitness value according to how well it solves the program. Create a new population of programs, copy the best existing ones, create new computer programs by mutation, and create new computer programs by crossover, so sexual reproduction, if you will. Genetic algorithms and genetic programming have been used to program a Pac-Man playing program, robotic soccer teams, network intrusion detection systems, and many others. All right, hopefully your heads are still attached to your shoulders. And with that, we made it. We made it all the way. Woo! I feel good. I hope you guys feel good. This is the end of class 11. Hope we're at this point we're done with the book. Now you guys need to study. We will be doing practice exams, I believe, this Wednesday. We start doing those with you guys. We'll have to figure out technical stuff in advance, so I'm shouting out to Brad and others that we need to get that figured out in advance, because if the three of us are going to present, we got to make sure we can do it right. It's so great to have all you guys here, and I appreciate you sticking with us, and actually quite a few of you on tonight. So hopefully you enjoyed this and you had a good experience. I look forward to seeing you on Wednesday at the practice exam. With that, I'm going to leave this up for a while, but everyone have a great night. Please do stay safe and continue to use the study group. It's been great, and we've had a lot of great results.